Cam mechanisms are often used to convert the rotation of the machine shaft into the desired movements of driven. In modern automatic machines, all movements in space are strictly coordinated in time. The right rhythm, trajectory and sequence of these movements are provided by cam mechanisms. Every cam mechanism consists of a pusher and a cam having variable curvature. The cam profile determines the movement of the pusher, changes the speed and direction of movement, and provides the necessary supports. During one cycle, the pusher performs several different movements, providing certain movements of the actuators. Cam mechanisms are very different. They can be simple with a cam in the form of a stationary slide, with a flat disc cam, with cylindrical cams, including end cams, and cams of a more complex shape, for example hyperboloid or canonical. Pushers receiving will have rectilinearly translational movements. Between a plane and a surface or between curved surfaces. To reduce friction and wear, the pusher is often equipped with a roller. The relative movements of the cam and the pusher may be different. Here the cam is moving, but now it is stationary, the pushers are in motion. One or another type of cam mechanisms is used depending on the specific design task. However, its implementation is possible only with continuous reliable contact of the pusher and the cam. At low speeds, this condition is met. But at a high speed of rotation, the contact can be broken. Continuity of contact is provided in different ways. By force closure by means of a spring. However, if the spring is weak, the roller contact may break. This happens when the speeds exceed the calculated ones. To eliminate the separation, it is necessary to increase the force pressing the roll to the cam, and this is not profitable, since wear increases. Therefore, kinematic closures are used, for example, with the help of a grooved cam. Changing the direction of rotation of the roller when moving from one surface of the groove to another is a disadvantage of such a closure. Closure is common with the help of paired cams with a double pusher. The cams alternately drive the pusher. The contact is reliably maintained even at high speeds. With this type of closure, sometimes two rollers are in contact with one cam. Frame closures and the closure of pushers between two cams on parallel shafts are also used. In properly designed cam mechanisms, the contact of the roller and the cam is not broken. Let's trace the dependence of the pusher movement on the position of the shred. Rise, expose, lowering, expose again. This is a graph of the pusher movement in a function of time. Differentiating this dependence, we obtain the pusher speed. Differentiating the speed, we get its acceleration. The totality of these dependencies is called the theoretical law of motion. Knowing this law, it is easy to calculate the cam profile. The theoretical law of motion is precisely fulfilled only in slow-moving mechanisms. The productivity of machines often increases due to an increase in speeds, but the higher the speed, the more clearly one of the disadvantages of cam mechanisms manifests itself, the negative effect of the reverse movement of masses. This is the elevator head of a strictly casting machine. Take a closer look at the nature of her movement. After stopping in the lower position, it makes a small oscillatory movement. This happens as a result of the elasticity of the links. Let's take a closer look at this phenomenon. At low speeds, the pusher moves with accelerations close to theoretical. As the speed increases, the actual acceleration already differs from them. The higher the speed, the greater these differences. Elastic vibrations appear. The reason for them is the deformation of the links. Cam mechanisms cannot be considered as mechanisms with absolutely rigid links. The cam profile must take into account not only the theoretical law of motion, but also the possible deformation of parts at the expected speeds. The law of motion of a mechanism with such a profile is called polydynamic. However, only a modern electronic computer can calculate it, which prepares the performance for a machine with software digital control. He makes a cam with the right profile. Externally, it differs little from the usual one. However, the oscillogram shows that the accelerations are close to theoretical, and the fluctuations at standstill are small. This is especially noticeable when comparing the periods of standing with a similar mechanism with the usual law of motion. The polydynamic cams operate reliably at the highest design speeds. When the links of the cam mechanism come into contact, significant contact stresses occur, therefore, large cams have to be used under heavy loads. But more often cam mechanisms are used in those types of industry where heavy loads are not required in printing, textile, food. Recently, they have been used in command apparatuses and pneumatic and hydraulic control systems. The widespread use of cam mechanisms is due to the possibility of obtaining any law of motion with their help.